Okay, so in this video, we're going to be looking at scales of measurement, specifically nominal, ordinal, interval, and ratio data types. So the first one that we want to take our look at is nominal data. So nominal and ordinal kind of go together, and they're both typically talked about in terms of their categorical data. Okay. And with the nominal types, this is data that has no inherent order. So, for example, if you're looking at a bunch of colors, you can see over here, right? I've got a bunch of colors here. Green is not inherently better than purple, which is not inherently better than blue, which is not inherently better than orange, right? There's no inherent order when you're trying to list different colors. The same thing can be said, for example, if you're looking at like flavors of ice cream, like chocolate, vanilla, or strawberry, right? There isn't an inherent order of goodness or whatever. Although I do think that chocolate should probably come first, but that's just personal opinion, right? Anything that can be like, any order that can be ascribed to personal opinion is going to be a nominal data set because there is no inherent order. Other categories or types of categorical data that fall into that, gender is nominal. Race is also a nominal variable, right? There's no inherent order for those types of categorical variables. Now, the same isn't true when we look at ordinal variables. Hence, right, ordinal has the word order hiding in it a little bit. So this is data that does have an inherent order. So examples of these types of things are, for example, like levels of education, right? Someone who has an associate's degree, that's a higher degree than a high school diploma, or a master's degree is a higher degree than a bachelor's degree or an associate's degree, right? Those things, those types of categories, there is an inherent order hiding there. Same thing can be said of, so this is a semantic differential scale from very unsatisfied, unsatisfied, neutral, satisfied, very satisfied, right? You see these types of things in surveys all the time. That's ordinal data, and we've built this inherent order into the question itself. And then the last example that I have for you is grades, right? An A is better, more desirable than a B, than a C, and a B is better than a C, right? So even though these are just letters, right, there is an inherent order hiding inside of these types of data, right? So you have nominal data, you have ordinal data. They're both primarily categorical types of data. One of them has order and the other does not. And so now moving away from the categorical data to the more quantitative, to the more numerical data, the first one in this category is interval data, okay? And your big descriptor here is that equal intervals are equivalent to equal distances. And so what that means is the example that everybody goes to with this type of data is temperature. And I'll explain why they use temperature in just a second. But let's say that we're comparing 20 degrees Fahrenheit to 22 degrees Fahrenheit. So the difference here, there's a 2-degree difference, right? And if I did the same thing, if I compared 80 degrees Fahrenheit to 82 degrees Fahrenheit, again, 2-degree difference, and that interval is the same. It doesn't matter if you're living up here or if you're living down here. 2 degrees between 20 and 22 is the same as 2 degrees between 80 and 82, right? That's what makes it interval. Just as a for example of something that breaks that, if you look at pH scales, so if you're into like how acidic something is, right? If something has a pH of 1 compared to a pH of 2, or if you're comparing these are like base 10. So this is a logarithm, like pH scales are based on logarithms, and so this is not a difference of 1, it's actually a difference of a power of 10 between those two things. And so you have to be really careful how you make comparisons in that, because the intervals inside of there may not be the same, because it's a logarithmic scale. It's not a linear scale like temperature is. Anyways, then the last objectifier here is that there is no true zero. And what that means is that in your data, in these numbers, right, because interval data is quantitative, right, it is numerical in nature, there's no true zero. What that means is when I say that it's 0 degrees Fahrenheit outside, this doesn't mean, it does not equal no temperature, right? 0 degrees Fahrenheit is just some random temperature on the scale, because it can be negative 20 degrees Fahrenheit. Not that we would want it to ever be that cold, but it can be, right? Negative values have meaning they have a real physical meaning in these scales, in interval scales. 0 degrees Fahrenheit, 0 degrees Celsius. They do not mean no temperature. Now, there is another temperature scale, if you've taken any science, called Kelvin. So this one is not interval, because Kelvin does have a true zero. That's why they use it, is because they needed a temperature scale that had an absolute zero, that zero actually meant no temperature. Anyways, so Kelvin does not fit into this idea, but Celsius and Fahrenheit do, because their 0 degrees is not a true zero. Okay, the way we look at our calendar year is the same thing, right? It is the year 2019, but if I go back in time to the year, so from 2019 to the year 0, that doesn't mean that was the beginning of time, or that there was no time at that point. That's just some marker that we have, that we decided to start counting up from there, because the calendar exists on the other side. Now these numbers, thankfully, are not negative values, but so calendar years on the negative side of the scale behave oddly, but the calendar year is a type of measurement where we can say, okay, look, there is not a true zero, and equal intervals are equivalent to equal distances, right? If we're comparing, 2 years today is the same thing as 2 years 100 years ago, right? That amount of time isn't any different. So those are the interval type values, and what you're really looking for is the true zero marker. Okay, is there a true zero in the data set? The last one is ratio data. And so this is data that does contain a true zero, right? And where negative values don't make any sense. For example, if you're looking at a person's weight or a person's height or their physical measurements, those are ratio scales, because number one, they do have a true zero, right? If something were to weigh 0 pounds, it wouldn't exist, right? Denoting that it actually has a weight means that it is present. Same thing with measurements, right? If something doesn't exist, you can't measure it, right? You can't have something that's 0 inches long, because it wouldn't be there. So in that sense, right, these things, and I think that that's easy to kind of wrap your mind around, that they're being, okay, so that does have a zero value. Another thing we can look at is income, right? Income is a ratio scale. It has a true zero. You can get paid $0. That's a really sad income to have, but you could get, right, that could be your income. And it actually means that it doesn't exist, right? 0 means that there is nothing of it. And it also doesn't make sense to have a negative income. Or, I don't know, maybe there are, you would never go and get a job where they said, okay, in order for you to work for us, you have to pay us, this many dollars per hour for the privilege of working here. That doesn't make sense, right? You don't have negative incomes. Some people may have, negative bank accounts because they have lots of credit card debt or whatever. But that's not the same as income. And then the last thing, I have this image, age, right? You're 10 years old, you're 30 or 40 or whatever. There is a true zero, right? There was a point in time where you were 0 years old, right? Where you didn't exist. And so age is a ratio scale, or fits into that idea. And so if you're trying to differentiate between interval and ratio, look for the zero, right? What does zero mean in that data set? If it means that the thing doesn't exist, then you're dealing with ratio. If zero in the scale is just another number like it is with temperatures, then you're dealing with something that's most likely interval in nature. Last thing for this bit, I wanted to look at discrete versus continuous variables. And so when you're dealing with discrete variables, you have a small set of possible values. And I've given a couple of examples here and just to try and explain these. So for example, with gender, you may say, okay, I'm going to consider 3 different possibilities. I'm going to consider, in my survey, I'm going to say, okay, if you're a male, put 1. If you're a female, put 2. If you're other, put 3. Or so right, but there's a small set of possible values hiding inside of the gender variable. Marital status is a yes or a no, right? It's a 1 or a 2. If you're trying to assign a number to it. Same thing if you look at, for example, number of chairs in a room, right? There, if you, not that this would ever be a part of your study, but if you were looking, right, there is a discrete number of chairs. You can't have 15 and a half chairs in a room. There's either 15 chairs or there's 16 chairs, right? There's no such thing as half a chair, right? Those are discrete values. Then the other type of value here are continuous variables. And with continuous variables, these are variables that can take on any value. Examples are speed, amount of rainfall in a month, temperature, meaning that you can be going 15 miles per hour or 16 miles per hour. You can also be going 15 and a half miles per hour. You don't jump from 15 instantly to 16, right? There's a continuous range between those two speeds. Same thing with amounts of rainfall. You can get half an inch of rain. You can get 3 inches of rain. You can get 3.5 inches of rain, right? It can take on any value. Temperature is the same. So when you're thinking about, often, we'll be looking at or imagining to ourselves okay, I want to do a study and I need to decide what types of variables I'm going to be using. And sometimes you'll be looking at things, you'll be and you'll need to decide, okay, can I even calculate a mean? Can I calculate an average? So for example, if you were doing a study with gender, and if you had assigned numbers, so let's say that you said, okay, female is 1, male is 2, other is 3, or you could have, right, there's a whole range of values you could have. It wouldn't make sense for you to take those discrete numbers and then at the end of your study average them, right? That wouldn't make any sense, right? You don't take a mean or you don't do an average with discrete values. That data just doesn't make as much sense to do something like that with. Or marital status, right? If you're looking at something where you could say that a yes is a 1 and a no is a 0, or a 1 or a no is a 2, it wouldn't make sense for you to add up all of your results at the end and average that, right? So when you're dealing with discrete things, you need to be really careful what mathematical operations you're going to do on those types of variables, right? Especially when you're assigning random values to different categories. Continuous variables, on the other hand, it does make sense to take averages of those things because an average has a physical meaning within the data set. So keep those things in mind as you're deciding and working on the different studies and things that we'll be looking at in the course.